And here we are. It's the physics video lecture. Physics 203, video lecture 12. Okay, we're working the central force problem, and I ended the last lecture with a simple derivation, or not derivation, deduction of Newton's law of gravity. In that case, from his laws of motion on the one hand, and Kepler's laws on the other. And we're going to do the rigorous version of that this time. So let's call this deducing the force law. So we'll say the central force from the orbital equation. We can put the basics up here. Namely, we have, this is what we had worked with, minus alpha over r. We have L is equal to m r squared phi dot is constant, and conservation of energy and the basic formalism gave us r of phi is equal to p over 1 plus e cos phi. Parameter and eccentricity we know. They're constants and on a lot of things. And the result was we would have the orbital exaggerated sufficiently, x and y. The angle phi with respect to one of the foci, which is just at the origin here, so that the geometrical center of the ellipse is not at the origin here, okay? But rather that's the sun at one focus, and we have Kepler's three laws. Kepler, I'll just write briefly. We've got the ellipse. We've got the law of areas, which really is just this. Turns out to be the same as the conservation of angular momentum. R squared phi dot. And the third law, we have the time squared proportional to, it's not an equal sign, period squared proportional to semi-major axis Q. And there's the semi-major axis right there, 2 times A. Okay, so we want to get this force, this one right here, given the r of phi. That's the idea. For this we need the equations of motion. And I was going to derive those two acceleration formulas. So we have m acceleration in plane polar coordinates and m acceleration, so radial and angular acceleration in plane polar coordinates. Of course, the second one is 0. But what we're going to do is just take the Lagrangian, the central force Lagrangian, because then we know the Euler-Lagrange equations give us the correct equations of motion. Okay? So we don't have to go back to those expressions or derive them separately. So we have a half mr squared phi dot squared minus u of r. Okay. So the Euler-Lagrange equations, and got enough room here to the right, so I'll just start. So we have one for r, and we have one for phi. We'll take care of this one here first. dl d phi dot minus dl d phi. Because we remember that, and we see here, phi is a cyclic coordinate, so that vanishes. And therefore dl d phi dot is constant. That means mr squared phi dot equals L is constant. That, of course, is the angular momentum. Got to write it right up there as well. What about this equation? this derivative here, time derivative, we're going to have m, our second derivative. That is this expression here. Actually, you know, let's ditch this. It's misleading. Okay. I'm going to erase that. Yeah, we're just going to follow the derivatives. So this is going to equal dl dr. Here we have mr phi dot squared, and then we have minus du dr on that side as well. And of course, this is the f of r. Okay. That's up there. Yeah, this intermediate thing was misleading. We'll go back to that. Okay. So we now can take this expression, we're going to use this, of course, into that first line, mr second derivative equals mr squared. Now the phi dot is L over mr squared. Lose that m there. M. What's more we feeling here? Equals mr. So the phi dot is the L over mr squared. L over mr squared. Quantity squared. That's better. Plus the f of r. So here's what we're going to be working with. Cancellation of a mass, so minus L squared over mr cubed. Masses cancels, r's cancels, equals f of r. Okay. So our task now is to take this and plug it in down here and then get the force law. But the thing is, we have r of phi, and here we have r of t. So we're going to have to do some manipulations of the chain rule. We'll just formulate what we're doing here on the right side, and then we'll go ahead and have at it. Okay. So we have r of phi, but since we have r of phi of t implicitly, we can just take two complete time derivatives of this thing, and whatever comes out there will replace, and then this expression will give us the force law. So r dot is equal to r prime times phi dot of the chain rule. So equals dr d phi dt. So that's what we're going to do. The second derivative will take a little more effort, but then we'll get there. So we'll just leave this up here. This board ought to suffice. Good, so let's start with that. So now, r equals r of t. R dot is equal to r prime of phi of t times phi dot. But that's r prime, which is dr d phi, times the phi dot that we have here, which is L over m r squared. Okay, that's the phi dot. So now when we take the second time derivative, gotta be careful here, we get an r double prime and a phi dot again as an inner derivative. The phi dot is L over mr squared, so we end up with L over mr squared. And then we're going to have plus r prime, and then here we have r squared in the denominator, so minus 2 over r cubed, L over m, okay, so minus 2L over m r cubed, and then we've got the r prime, and we have the phi dot again. So yeah, you got to be careful with that chain rule, and the phi dot is again L over m r squared. So now we just have to clean this up, and let's see if we can do everything at once. So m r double dot would be equal to m r double prime L squared over m squared r to the fourth. Minus 2 r prime squared. What's that? M L squared over m r to the fifth. And this we're going to plug in to this expression right up here. Let's factor out, got an extra power here, let's factor out an L squared over m r to the fourth. Okay, so L squared over m r to the fourth, that leaves us just with r double prime. So L squared over m r to the fourth. Looks like we've lost the power of m up there. M squared. M squared m times. So there was another m here. So L squared over m r to the fourth, we end up with minus 2 r prime divided by r. And then this last one here, L squared over m r to the fourth, we're gonna have to multiply an r again. Okay, let's see what the power I've got there. Yes, minus r. Minus r, good. Equals f of r. So there's our recipe. If we have the r of phi, given r of phi, r prime is dr d phi, then we go ahead and work this through and we find whatever that force law is. So I'm going to do the easy one and leave the good one for you guys to do. Let's consult here, make sure we got the m r to the fourth. Fantastic. There we go. So that's the expression for the force law. In fact, I'll write it the other way around just so we have something to look at. So f of r, which is what we're looking at, we take L squared over m r to the fourth, and then we have second derivative was a squared here. Yeah. Minus r. Good. And you know, I'll just formulate the homework right now. Homework. What we want to do, of course, is Kepler's law of orbits. From r of phi equals p over 1 plus e cos phi, deduce that f of r is proportional to 1 over r squared. This is general enough to cover all of the conic sections, so not just the ellipses, but the hyperbolas and the parabola as well. So that's the homework, and I'll show you how that's done. In a basic version here. So our example is a spiral. So suppose r of phi is equal to c times phi squared. That would mean that as we leave the origin, we're spiraling out. Okay. Or we could also be spiraling in, right? That's not what we said. Spiraling out or in, but as phi increases, the radial distance increases like this. Okay. So r is equal to c times phi squared. Now let's go ahead and take a couple derivatives. R prime of phi is equal to 2c times phi, and r double prime of phi is equal to 2 times c. Of course, c is a constant, right? So now we're going to plug these in. Now, f of r, this gives some really unusual stuff. Let's just go ahead and write this out. So we got L squared over m r to the fourth. The second derivative is just the 2 times c. We have minus 2 over r. And we have r prime squared, which is 4c squared b squared minus r. So we're not done yet. We have to eliminate the angle phi from this expression, which is not hard to do. L squared over m r to the fourth. We got 2c. We got minus 8 over r. And now we have c squared phi squared. Now phi squared, so we have a c here. Now c times phi squared is r. Okay, so we got pull out one of the c's, and c times phi squared is r. And then we have minus r. So you can see how this is going to simplify. We have 2c minus 8 times c. 2c minus 8c. The r's cancel. So we have L squared over m r to the fourth. We're going to simplify this one more time. So minus 6c minus r. Good. Now what about the dimensions here? Well, they're right, because the angle's dimensionless, so c has the dimensions of a radius, okay, of a length. So let's simplify this thing one more time just to see what we have obtained. So in particular, here's what I want to give it. So the force law is, we have minus 6c L squared over m r to the fourth, and then we have minus L squared over mr cubed. So that'll work. Minus sign on both sides. So that's an attractive force with the minus sign. And what is it? It's a 1 over r to the fourth and a 1 over r to the third combination. Turns out that any power of r greater than 2, do we have any 2's up here? No, we don't. Any power of the force greater than 2 has these spiraling type of orbits of various types. And what you also see here is finding the orbit from a force law can of course be a whole lot of work, but finding the force law from the orbit can be pretty easy, and you find a lot of interesting things. So yeah, here we have a combination of 1 over r to the fourth and 1 over r to the third, and that is a spiral orbit, okay. Attractive force, something will spiral into the orbit. Yeah, so having said that, let's come back to your homework assignment. And consult here. Yeah, that's good. Okay. So let's think about this a little more. We have to do some differentiating. This is going to take a little bit of work. You've already got the L squared over mr to the fourth, so you have to take those two derivatives, and you'll have 1 plus e cos phi to the minus second power with an inner derivative, minus e sine phi, that type of thing. For the first derivative, you have to take a second. So once you have those all out there, you have to eliminate any last vestige of the cosine of the angle phi. Okay. So you do all those derivatives, then you have to do enough trig, whatever it takes, to get rid of cosine of phi. And you're just left with powers of r. And in fact, this one works. You're going to end up with a factor in front, 1 over r squared, and in fact you're going to obtain the minus sign as well. The minus sign is crucial because we're talking about the attractive problem for this Kepler orbit here. Okay, so yeah, deduce that, including the minus sign, and you'll have some constants with angular momentum. If you want, you can reduce those as well, because when all is said and done, it should be minus alpha over r squared. F of r equals minus alpha over r squared. Okay, that's pretty satisfying once you're done with it, of course. Good, so that's a homework problem. And these you can actually just play around with. You could do a linear one, you could do a higher power. Whatever you're able to then reduce to a simple expression like this, you get those powers. Okay, let's consult the clock. So, we now have a couple more topics in central force, then I want to move on to Hamiltonian mechanics. But one more very important topic with circular orbits. Okay, so this section is called nearly circular orbits. Yeah, it's very germane. Many planets have very close to a circular orbit, and satellites can, of course, be launched with arbitrarily accurate circular orbits. And there's some interesting things that come out of this. So we're talking about circular orbits and nearly circular orbits. So circular. Let's look at our effective potentials again. So we have our energy expression, 1/2 m r dot squared L squared over 2m r squared U of r is equal to E. So we're back to the expression that we used to integrate the differential equation and find the Kepler ellipses. So as you'll recall, so this is the energy. We're in plane polar coordinates. This is the effective potential. And has a very characteristic graph for the Newton potential. So I'll just call this U effective R. And in particular, we know that it's at the circular orbits that the effective potential takes on its minimum. So I can call that E0 and R0 for the circular orbits. Yeah, so for circular orbits, U effective prime of R0 is equal to 0. First derivative criterion. And there's U effective. Let's go ahead and do that. So U effective is L squared over 2mr squared plus U of R. And we take its derivative, and we have minus L squared over mr cubed right here, right? Plus U prime of R. And good, that's the derivative at the location of the circular orbits. The derivative vanishes. So we have, continuing this thought, circular orbit now, we have U prime of R is equal to L squared over m R naught cubed. Okay. And we have L is equal to m R naught squared phi dot. Okay. Remember, when we write this energy down, we're also using a conserved angular momentum. Right? We made that substitution here to get this expression. So we get the conserved angular momentum, and we can plug that in here. So we have m R naught squared phi dot. We're going to square that over m R naught cubed. And let's see what comes out here. We have m squared R naught to the fourth phi dot squared over m R naught cubed. Now here's the thing. This simplifies nicely. We end up with a mass. We get 1 power, and we have phi dot squared. I'm going to refer to this as omega sub phi squared. The reason is that we have a conserved angular momentum, we have a constant radius, therefore this phi dot itself is constant. Okay, this angular velocity is constant, and I'm renaming it to omega sub phi squared. And again, since we have circular orbits, I can do the following. I can have m r naught, and then this omega sub phi can be written as v over r naught. Okay. Remember, you have omega sub phi, r sub naught would be v, and that would just be the velocity of the speed in the circular orbit. Okay, so the omega would just be v over r, square it, and we end up with an m v squared over r naught. And of course, that's a familiar expression too. That's the famous mass times centripetal acceleration. So that all comes out of the formalism nicely. Okay. So the circular orbits, we can check them off, so to speak. Okay. There's nothing. Yeah, and actually, so this was u. Can't throw it that way. This was u prime. Okay, so u prime is of course the magnitude of the centripetal force, because this is the magnitude here. The minus sign would have come in, indicating that it's pointing towards the origin. Okay, this is the magnitude of the centripetal force. Okay, so that's all working out nicely. Now, the next thing is to consider energies E greater than E0, but retain the conserved angular momentum. But L remains constant. So first you want to ask yourself, how can one do that? So imagine you are in an orbit. You're in a circular orbit. Here's the center. I'll put a star there. That's the center of the potential. If you want to retain the angular momentum and increase the energy, so this is just kind of an interesting practical question. How to increase energy of orbit but retain angular momentum. In other words, retain the same value of the angular momentum. Question mark. How to do that? Well, so we're in our satellite here, we're orbiting, and we could do two things. We could fire rockets tangential to the orbit, tangent to the orbit. That, of course, will increase the angular momentum. On the other hand, we can fire the rockets towards or away from the center of attraction, and then our force is parallel to our, so that the added force is parallel to the central force. Okay, and that leaves the angular momentum unchanged. So that's the answer to that question. If you want to change your orbital energy and keep the angular momentum the same, you fire towards or away, because that is a central force itself, right? The central force retains the angular momentum. Central force has a conserved angular momentum, and that is the same thing if you're using your rockets blasting centrally. Okay, so what happens then is we've done that, and we've increased the energy now to some slightly higher level. So it was E sub 0, now it's a little higher. And going back to our original discussion, we now have R min and R max. So for E1, we have an R min and an R max. And now the question is, what kind of orbit is it? Well, that depends. If this is actually the Kepler problem, okay, this is actually 1 over R potential, then we just know that these orbits are going to be closed. They're actually going to be ellipses. But if it's not a 1 over R potential, then we don't actually know, just without doing some work, whether or not it's a closed orbit. So we're going to talk about closed orbits. Okay, good. I'll probably reproduce some of this board. So we're now at the stage where we started with a circular orbit. Given it a little extra energy, now we have a nearly circular orbit, which for the Newton potential is just an ellipse. Otherwise, we're not quite sure what it's going to be. Okay, so let's continue on with this. Because I'm going to reproduce this up here with a little more room on the board. So we have that effective potential. We have R sub 0, E sub 0, and again, get a little extra, I'll call E sub 1 is equal to E sub 0 plus some little delta E. And there are now R min and R max. And because of that, so for E equals E sub 1, the orbits take place between R min and R max, so we can actually draw two circles. This is the minimum, and out here is the maximum distance. Now here's the thing. With the Kepler problem, if you're doing an orbit and you start at R min, you end up at R max when the angle is pi. When the angle of pi has been swept out. Okay? But that needn't be the case generally. So let's put these words here. Motion is restricted to this annulus here. Annulus R min less than R less than R max, we could say less than or equal to. Right? The orbits are not generally closed. Not generally closed, and it becomes interesting to find out what is the area, not the area, what is the angle here swept out every time you go from R min to R max. So C is the angle that's swept out. It's called the apsidal angle. Swept out between R min and R max. It's called the apsidal angle. from the advance of the apsids. Apsidal angle. And again, Kepler problem, that is equal to pi. So we're gonna get a general expression for this thing, and of course we're gonna make sure the Kepler problem comes out pi as well. All the apsidal angle. Now, in general, the calculation of this thing could be difficult, but there's a case where it's very basic, and that is if the orbits are nearly circular. That is to say, this energy difference is very small, so R min and R max are very close to R zero. Of course, we're going to keep our picture with them adequately separated so we can think about the problem. But the case we're actually looking at is when the orbits are nearly circular. Okay, let's consult the clock. Very good, we got this. So, nearly circular orbits. So when orbits are nearly circular, C can be easily calculated. Yeah, so when the orbits are nearly circular, then we are very close to R sub 0 at a local minimum, comma, because R sub 0 is the local minimum of U effective of R. Yeah, we have a local minimum. The effective potential, the whole idea was it was effectively a one-dimensional problem, and we can think of the small oscillations about that local minimum. So small oscillations of R near the local minimum. Okay, we can just write that down. Okay, this is a one-dimensional problem. We have R of t is equal to R0 plus some little letter A for amplitude, cosine of omega sub R times t. Okay, we don't need to have any other phase information in there. Okay. A is very small, so we're very close to a circular orbit, and omega sub R is simply the effective potential second derivative. Okay. Just as the frequency is always called, the second derivative of the potential divided by the mass. Here's the second derivative of the effective potential divided by the mass, because that's why we have effective potential in the first place. Okay, we're right around there, and we're fitting, remind you guys, we are fitting a parabola into that curve. Okay. Good, so we have this here, we have an omega sub R. So under these circumstances, now I can define C as 1/2, or actually let's write it this way, as omega sub phi times 1/2 p sub r. So let me explain what that is. This omega sub phi we had a little while ago, that was the angular frequency, angular velocity of the circular orbit. Okay. So if I draw this picture again, actually I have a good one up there, I'm just going to point to it. So imagine we have this object here. It's now going to start its orbit, and what color will we use? We'll use red. It's going to sweep out and reach its maximum distance right there. Okay. So it's as though we had a counterclockwise motion, okay, and the frequency of that is omega sub phi. But the T sub r is the period, or yeah, the T sub r is the period of an oscillation from r min, r max, and back again. So half of that period is the time it takes to go from r min to r max in the radial equation. So yeah, we just combine those two. Omega sub phi 1/2 T sub r. So that gives us the apsidal angle. And as accurate as you would ever need for these slightly perturbed orbits. So we take it as a definition. And because omega sub r T sub r is equal to 2 pi, just on general principles, we can write this in a different way. C is equal to omega sub phi over 2, and then the T sub r is 2 pi over omega sub r. So we can also call this pi omega sub phi divided by omega sub r. And this is the one we're going to use in our general calculation. And you know, I think I'm going to do the whole thing right now. Let's see how we're doing time-wise. Yeah, we got nothing but time. Okay, so what we want to do next is calculate this expression once and for all. We get a really interesting result. And you know, before I calculate, I'll say a couple of words about why we're doing this. Okay. Turns out that the potential energies, even in our solar system, are not truly 1 over r squared. Okay. The 1 over r squared law of Newton is true for a truly spherical symmetry, but their bodies are rotating, and therefore they're not true spheres. And what happens is you get small corrections to the 1 over r potential. Small corrections to the 1 over r squared force law. Those small corrections give you small corrections to this angle, which will otherwise be pi. And those corrections can be measured very accurately by observing satellite, planet, and other orbits. And from those things, you can infer things either about the law of gravity, whether it's true or not, or you can infer things about the structure of the central body that's being orbited. So, yeah, so this continues to play a big role, and historically it's played a huge role. So, but first things first, we have to actually calculate this and reduce this expression here to something in terms of the potential, which isn't up on the board now. So let's have a go at it. Our next task is just a general calculation of this apsidal angle right here. Yeah. So we are going to analyze the effective potential. So let's see what we have here. We have U effective R L squared over 2m R squared plus U of R. And we're going to take, and we'll take two derivatives. U effective prime of R is equal to minus L squared over m R cubed plus U prime of R, and U effective double prime of R is equal to 3L squared mR to the fourth power plus U double prime of R. Okay, next we have to look at what this expression for C means. We can rewrite it as follows. C is equal to pi over, not so fast, omega sub R divided by omega sub phi. That's going to be handy. And we have omega sub R is equal to U effective second derivative of R0 and omega sub phi is going to come out of, is equal to, let's see, remind ourselves where it comes out of. So we have m R squared phi dot is equal to L. So m R naught squared omega sub phi is equal to L. So it comes out of this equation right here. That's where the omega sub phi comes out of. So we're going to put these things together. I could even assign this. I'm running out of time. But let's do it right now. So from this first equation here, we have U prime of R naught. Okay, so move from equation number, U prime of R naught is equal to L squared over m R naught cubed. And then from the second equation, we have U effective double prime of R naught is equal to 3L squared over m R naught to the fourth. So we can say we have 3 over R naught U prime of R naught plus U double prime of R naught. Okay. So we have this thing right here. And finally, we have to remind ourselves what omega sub phi was. And omega sub phi was L over m R naught squared. So all of these ingredients should come together now. So let's see, we have C is equal to pi divided by the omega sub R is this one right here. Square root of 3 U prime And in fact, it's going to be m r naught plus u double prime r naught divided by m. And then the omega sub phi here, L over m r naught squared. Actually, we want u prime of r naught is equal to m r naught omega sub phi squared. So right now we have, with the omega sub phi up here, we have to take it in as a squared under that square root, and then keep working. So now we have pi square root of 3 u prime of r naught over m r naught plus u double prime of r naught over m. And then if we're going to divide by the omega sub phi squared, then we have omega sub phi squared is equal to u prime of r naught over m r naught. So that's what we substitute by. U prime of r naught divided by m r naught, and simplify. And we end up with pi root 3. Everything cancels on this one here. And here the m cancels. U double prime of r naught times r naught divided by u prime of r naught. Okay. So this is fantastic because we've eliminated everything except expressions involving the original potential, the actual potential of the problem. So we have u prime and u double prime. So having done that, I'm going to go ahead and showcase this again. First I'll consult the clock. No problem. Good, so we have, this is our result. So let's go ahead and put all this stuff together now. In fact, I thought we'd put it all together. Absolute angle nearly circular orbits. So we start with the central force problem. So we have Newton's law. Before we did anything, right? Central force problem right here. U of r is just minus integral f of r dr like that. So if you have one, you have the other. And then we have our circular orbits. And now we're talking plane polar coordinates. And for the circular orbits, we have conservation of angular momentum. So m r naught squared omega sub phi is equal to L. So that's the constant there. We have the effective potential. And when I draw this generic form, of course the Newton potential is the most effective potential. That is the most important. That's where you have the R0 the R min and the R max. And that's where you have your motion taking place inside of an annulus here. And I'll draw what happens. So suppose you had an apsidal angle that's less than pi. So when you come out to here, and the next time you go around, come back inside right there. And you know, if you have a really fast hand, you can, yeah. I used to be able to draw these better than I can now. So you can have these orbits actually fill out all of the space between the two radii. Okay, so now we have C is equal to pi divided by root 3 plus u double prime around the circular orbit times r naught, u prime of r naught. So we have to try, first of all, a couple of examples. Force minus alpha over r. This one we have to try first, right? U prime of r is equal to alpha over r squared. U double prime is equal to minus 2 alpha over r cubed. So we'll just go ahead and plug those in. We get pi divided by root 3 plus, and now u double prime times r, we get a minus 2 alpha over r squared, and divide by alpha over r squared. And you see you get these cancellations, and it's 3 minus 2. So it's pi divided by 3 minus 2, which is just pi. Okay. So the Kepler orbit has this apsidal angle of pi. That means it has closed orbits. That doesn't change. But you can also see now that inescapably, as soon as you're away from this 1 over r potential, strict 1 over r potential, you're going to be away from this strict 3 minus 2 equals 1, and you're going to start having these small differences in the angle. So I'm going to assign a couple of problems now. Actually, the first one's trivial, but let's put it on your plate so you go through with it. So calculate C for U of R is equal to 1/2 k r squared. That'd be a harmonic central force potential. And sketch the trajectory. Sketch the trajectory between your concentric circles. This one's interesting because it is a closed orbit, but the apsidal angle is not equal to pi. Okay. So by sketching that and thinking about it, you'll see what's going on there. Okay. And the second part here is, suppose U of R is equal to minus alpha over R plus some beta over R cubed. And beta is small. Well, first you have to figure out what does it mean for beta to be small, right? This is sort of a perturbation to the 1 over R potential. And in fact, it's what comes about when you have an oblate spheroid. So say you have a rotating body, instead of a sphere, it's flattened out a little bit because it's it's a celestial body, it's a rotating gas. And even our Earth, not a rotating gas, but it's ever so slight oblate spheroid. What happens then is if you expand the potential and powers of 1 over r, you find this next contribution. A perfect sphere has minus alpha over r, an oblate spheroid has a little extra here. So I'll just write here oblate spheroid. This will be a good one to discuss in the office hours too. It's a good problem. So beta is small. Calculate C. Now, what you're going to find is you can't actually even figure out the exact r sub 0. It doesn't really matter. You calculate this thing here. You'll have 3 plus some stuff plus another term. And what you do, because this is small, you essentially expand this square root. Okay. Expand the square root, so you'll end up with pi plus some smaller quantity that involves beta and alpha. So here's an important note. You're making use of the fact that 1 plus x, square root of 1 plus x is approximately 1 plus 1/2 x. That's just the Taylor expansion. That's a 2 right there. 1 plus 1/2 x. So this is a really important problem because for example, Mercury has some absolute angle that's different than pi. And some of that comes from this classical calculation, and some of it comes from general relativity. So this had to be very well established and understood before the general relativistic contribution could be dealt with and discovered. Okay, this is a good place to stop. You calculate this thing, it's going to be an approximation. You're not going to get an exact pi, you're going to get pi plus something else. Basically, you pull out this part, and whatever's left is your x, and you got 1 plus 1/2 x. Okay, denominator 1 minus 1/2 x. Okay, I'll leave that for you guys to do, and we will see you next time.